Hi class, this section is about rational functions and their graphs. We're going to be working on horizontal, vertical, and then sketching. We are not going to have perfect graphs. We're not going to worry about turning points. We just want to know where they're at and how they work. So get your notes out and let's go. All right, we're going to identify the domain and range of the rational function. We are going to work on the vertical and the horizontal asymptotes. We're going to look on, once we know a parent graph, how it moves, its transformation. We're mainly going to focus on rational functions, and we're also going to identify slant asymptotes when it doesn't have a horizontal, and we're going to do a few story problems with these. So when you look through here, a rational function just means it's in the shape of a fraction. So you have a function over a function. Okay, when you do a function over the function, the denominator can never be equal to 0, because that's when you divide by 0, and that's undefined. So we always look at the denominator first. So we set the denominator equal to 0 and we solve. These will be your vertical asymptotes. Okay, it's what the vertical cannot be. So this truly means x cannot be equal to 5 because that makes it undefined. Interval notation. So if we're on a number line and we're at 5, that means I can go from negative infinity to 5, but I can't include 5. And then I can start at 5 and go to positive infinity. So that is literally what your interval notation looks like with a union sign in between. Set builder would just say it cannot be equal to 5. All right, let's go here. Sometimes we will have more than one solution. So try yours, pause, and go. So this one is x plus 1, x minus 1, and that means x cannot be equal to a negative 1, and x cannot be equal to 1. When you do these all in the number line, so we have negative 1 and 1 cannot be equal to from negative infinity, that's a terrible infinity, to 1, from negative 1 to 1, and then from 1 to positive infinity. And that's exactly what your interval notation would look like. You would go negative infinity to negative 1, union 1, no, sorry, negative 1 to 1, union 1 to infinity. Then again, set builder is exactly this. It would be x such that x cannot be equal to negative 1 and x cannot be equal to 1. Okay, your bottom one, I hope you messed up right here because x squared plus 25 is unfactorable. So when you tried to solve it, you had x squared equals a negative 25. So you had x equals plus or minus 5i. Well, since this is imaginary, it doesn't belong on our number line because our number line is only real numbers. So it goes from negative infinity to positive infinity. Set builder would just be all real numbers. You would write it out. X such that x is an element of the reals is how that looks. Okay, we're going to work on asymptotes. So you have x over x squared minus 1. Remember, always denominator. That's where we start. X squared minus 1 set equal to 0. We get plus and minus 1. So x cannot be equal to 1, and x cannot be equal to, whoops, I just made my plus and minus 1. So those are asymptotes or hole in the graphs. We're actually not quite sure right now. So I know it's undefined at those two spots. So I go to 1, negative 1, and draw a dashed line because it is not part of my graph. It is a boundary of my graph. Now we look at our entire one, and if it does not cancel, then I know they're two asymptotes. If it would cancel, that's something that's going to be a hole, and we will come up with next. You don't know how to graph this yet. You will here in about 2 seconds. But right now, I just want to know, make sure you can get those vertical asymptotes in. All right. Next one, x squared plus 25. Remember this here was undefined. That means it's always good on the x-axis, so there are no vertical asymptotes. Okay, try yours. You should have said x plus 2 equals 0, so you should have said this is at negative 2. So x cannot be negative 2 in my graph. So I have an asymptote here since it does not cancel. All right, we're going to get more fun, I promise. Horizontal asymptotes. All right. A horizontal asymptote is just like this. So we have an asymptote here. So this guy is approaching the horizontal from the bottom. This one here would be approaching the horizontal from the top. This one here actually crosses and approaches the horizontal from the bottom. We will show you how to find horizontal here in just a second. The easiest way to do it, and there's a great big long proof for it, but I always learned it. My calc teacher, actually a calc teacher I taught with, always taught it with a big H. He said H stands for horizontal, and the most important thing on the top goes up here, and the most important thing on the bottom goes in the numerator or the denominator. So we look here, and that's just the guy with the highest exponent. So this is 9x squared, and this one is 3x squared, and you reduce them. And this reduces to 3. So my horizontal asymptote is 3. So when it approaches, we don't know where. Okay, I drew it in for you just so you had an idea. It actually starts at 3, goes down to 0, and comes back up. It's really quite a cool graph. But the asymptote is still 3. Oops, sorry. Now, let's look at yours. That's when they were equal. The degrees are what the degree on the, okay, come on. If you looked here, they were x squared and x squared, so it canceled to a straight number. Now, when we do our horizontal, so we got the 9x in the numerator, the 3x squared in the denominator, this cancels to 3 over x. If there is an x in the denominator ever, I don't care what kind of number, there's an x left down there, so the degree in the denominator is larger than the numerator, it is y equals 0. So we go to 0 and we draw on our asymptote, and this is what this one looks like. It starts from negative infinity, it dips down and crosses the asymptote actually, and then approaches again from the top. Quite fun graphs. You don't actually get to do those. Ours are a little bit easier than that, but I want you to be aware they existed. All right, now if the degree of the numerator is 1 more than the degree of the denominator, so we go to reduce this dude, we're going to end up with 3x. This is an issue. All right, if you end up with that, you do not have a horizontal, you have what we call a slant asymptote. And pretty soon we'll show you how to create a line. So there's actually a line that's going through here. Ooh, that's really crooked. Like so, that this graph is following, rational expression is following. Okay, here we go. I want to find the horizontal asymptote, so pause and do these. This one you should have had 4x over 6x. Which is 4/6, which was 2/3. This one here, in your h, you would have put the 2x over the 5x squared. X was in the denominator, so that equals 0. This one, you would add the 9x squared over 3x, so the x is left in the numerator, so you would have put no horizontal. This is a slant asymptote. All right. Let's graph this thing. We're going to do everything now, vertical, horizontal, and the graph itself. So we always start with our vertical by setting the denominator equal to 0. So we got here, x minus 5 equals, so x cannot equal 5. So currently I know this is either a hole in the graph, which we haven't talked about, or it's an asymptote. In order to find out, I have to factor the top. So if I factor the numerator and it cancels, it is a hole. So now I go to x plus 2, x minus 5. This is this guy factored. Factors to 10 that give you -3. Well, the x minus 5s cancel. Well, this now makes this a hole in the graph. All right? So it means when it's 5, it doesn't exist, but we graph the actual new function that's left. So I'm left with y equals x plus 2, or f of x equals x plus 2. I'm hoping you recognize that's a line. So you go to 2 for your y-intercept, up 1 over 1, draw in your line. Okay, which is all fine and dandy, except this line cannot have a value at 5. So we go to where x equals 5, which is here, and you go until you hit the graph. So you either go up or down. This time we're going to go up. I will cross the graph here. So this is a hole in the graph. So it's like a break. So this line goes up until hits, oh, that was weird, 5, until x equals 5, and there's a hole, and then it continues on. Okay, let's look at this one. Now we're going to do first always our denominator. So the factors of -4 that equal 2 should be x minus 6, plus 6 and x minus 4, which means x equals -6 or x equals 4. I either have a whole or two asymptotes. So now I look at my horizontal is x over x squared. Oh, an issue here because this is 1 over x. So this here is a slant. Okay, now let's reduce. We have x plus 6 over x plus 6 times x minus 4. These cancel and we are left with 1 over x minus 4. Okay, now I'm going to graph this as is. So when I look at 1 over x minus 4, well, I know my vertical is going to be x equals 4. So we're going to go to 4, which we had right here, right? And we're going to draw in our asymptote. So he stayed an asymptote. 1 over x for my horizontal is 0. So at 0, I have a graph. Now I need to decide where it is. To do this, you pick a number on each side. So since this is 4, you pick a number to the left and to the right. So I'm going to pick 3 and 5, one to the left and to the right of 4. You plug this into your original, so you're here. So we're going to plug 3 in. So it's 3 plus 6 over 3 squared plus 2 times 3, which is 6, minus 24. So 3 plus 6, so we've got 9 over a negative 9. That doesn't seem right. 15, negative 24. Can't add today. Oh, and I'm making it too hard. This is what I was thinking. All right, let's try this again. Since I'm graphing the reduced equation, we can actually plug these into the reduced equation. So we're going to use 1 over x minus 4 to make my life easier. So this is 1 over 3 minus 4, which is 1 over -1, which equals -1. So we go to 3, -1, and there is our dot. It's underneath. So now we graph this by approaching the asymptotes. So it approaches this direction, and it approaches this direction. Now, let's plug in the 5. So we go 1 over 5 minus 4, which equals 1 over 1, which is 1. So 5, 1 is here. Again, you're following along on the asymptotes at your point, and that's your graph. But we have this, it cannot equal -6 part. So we go over to -6. Should have drawn a graph farther. Let's go like this. Okay, at -6, x is undefined. So I go to -6. I have to go down to hit my graph this time, and I put a hole in my graph. And that is your graph rational expression, or a hyperbola. All right, two parent graphs that you have are 1 over x and 1 over x squared. 1 over x are your asymptotes are on the y-axis and the x-axis, which makes sense. You set it equal to 0, and you get 0. 1 over x, x in the denominator, again 0. Then it's up 1 over 1 for your point where you turn, approach the asymptotes, left and right, and the same here. You plug in -1, you get -1, approach the x on the bottom, and the y on the left. You need to know that to help with transformations. X squared is the same thing, except now we have the x on this side, and since it's squared, it's no longer negative, so it moved up to the top. Still, asymptotes of 0 and 0. It's helpful if you know those two parent graphs. Okay, so this is an x plus 3, or 1 over x. So I know my parent graph is the 1 over x. Let's draw him in, just so we're remembering. So you got the y asymptote, x asymptote. We know it's at 1, 1, approaching from the top and approaching from the right. Here it's at -1, -1, approaching from the bottom and approaching from the left. Okay, there we go. That is my parent graph. Now this moves just like before. The -2 is now left or right. So I'm going to move on the y, -2. So I'm going to go down 2, which means my horizontal asymptote is now down 2. So it's y equals -2. So we go to -2 and we put in our horizontal asymptote. The vertical follows the same as before. So you put x plus 3 equals 0. So x equals -3. So it's going to move 3 to the left. And we're going to put in our vertical asymptote. Okay, now that we have these, there's no stretch, there's no number up here. So I know from here I went up 1 over 1. So I'm going to go up 1 over 1 for my first dot. Then I'm going to approach my asymptotes, the vertical and the horizontal, and the same with down 1 over 1, and approach from the bottom and approach from the left. And you are done. Okay, your turn. Okay, yours is an x squared, so you should have recognized your parent graph. You had the y-axis and the x-axis again as your asymptotes. This time it went through 1, 1, and it was up here just like before. But now the squared moved it from the negative to the positive, so it's now -1, 1. And that is my parent graph. Okay, now let's graph our moves. So +2 means it moves up 2, which means my horizontal is equal to y equals 2. So we go to 2 and we graph our horizontal in. Okay, x squared minus 3. So now we know we move opposite. So I know my vertical is going to move right 3. So I can go right 3 and put this in. Okay, there's no stretch. There's no number on the top. So I know it's 1 and 1. There we go, in the first one. And then in the second is the same. Goes left 1, up 1. And there we have our transformed graph. I hope you did well. Okay, we've talked about horizontal, vertical, and picking a point. So let's put this all together. First thing we're going to do, well, I would have started here first. X squared minus 16 equals 0. So we know this is x plus 4, x minus 4. So x cannot be equal to -4, and x cannot be equal to 4. All right, now we need to see if that's going to factor out or not. So 3x over x squared is my horizontal. Should have flipped these two. I always do this one first and this one second. So that's going to be 3 over x, which means there is no horizontal. We have a slant graph. Oh, sorry, I lied. That's when the 0 is on the bottom. That's we have a 0. So our y equals 0. So now we have a 0 here. Okay, now we got to check to see if things factor. So let's factor out the top. Take out a 3. We have x plus 1 over x squared x minus 4 and x plus 4. All right, nothing cancels. Since nothing cancels, both the 4 and the -4 are vertical asymptotes. So we're going to put one in at -4 and one in at 4. Now we have 6 sections to our graph. We have over here, we have the middle, and then we have the right. What we do is we check on all of these and see if they're on the top or the bottom of our horizontal asymptote. So we know that this here is at, let's get a different color, -4, and this is at +4. So I need to pick one to the left and to the right again. So -5, -3, 3, and 5. We're going to plug those 4 points in to our original, our right here, since nothing factored, and see if they are on the top or the bottom of the horizontal. So we're going to do -5. So all you're doing is you're plugging in -5 and you're finding y. So let's plug in -5. We have 3 times -5 plus 1 over -5 minus 4 times -5 plus 4. All right, -5 plus 1, that's a -4. So we have -12 over, this is -9 times a -1 over +9, which equals a negative divided by 3, 4/3. So we got a negative 4/3 here. So we go to -5, negative 4/3, and -1 1/3, which is right about there. And that's all we need because we only have two boundaries here. So with that point, I'm going to approach the y-axis from the bottom, and I'm going to approach -4 from the side. First part of my graph. Now to graph the middle, I need to graph 2 points because the middle has different options. It can look like a parabola going up, a parabola going down, or an S shape, and it can go either direction on the S shape. So I need 2 points in order to tell what shape I have. So we need both the -3 and the 3. So again, we're going to plug it into our original. So we have 3 times -3 plus 1 over -3 minus 4 times -3 plus 4. So we have a -2 here, which gives me a -6, and an over a -7. So we know -3 equals 6/7. So -3, 6/7, almost 1, first dot. So I need the second dot in order to figure out how to graph this. So now we plug in the 3, again to the same place. 3 times 3 plus 1 over 3, whoops, over, parentheses, 3 minus 4 times 3 plus 4. So this is 4, so now we have 12 over a -7, so this is -12/7, almost 2. Okay, I have one up top and one below the asymptote, which means it is sort of like that S-shaped thing. Please hit your dots better than I did. And now we plug in the 5, again to the same equation. So we have 3 times 5 plus 1 over 5 minus 4 and 5 plus 4. So we end up with 6. 18 over 9, which is 3 on the top, and finish sketching in your graph. I hope you did well. All right, now it's your turn. Pause and try yours. Okay, step 1. What is my vertical? We have 6 times x minus 2, which means x cannot be equal to 2. Now we need to know if that's a vertical or a whole. So we need to check. So next I'm going to find my horizontal first. 3x over 6x. That is equal to 1/2. So I know at 1/2 I have a horizontal asymptote. That's guaranteed, so I can draw him in. Okay, next I'm going to see if it reduces. So we're going to factor out the top. 6 times x minus 2. It does not reduce, so that means x cannot be equal to is undefined. It is a asymptote. Now I need to plug one number into both. So we're going to plug in 1 and 3. And again, I'm going to go just straight here. So we're going to take 3 times 1 plus 1 over 6 times 1 minus 2, which is going to give you 6 over -6, which equals -1. So at 1, we get -1. And make sure you go to the asymptote and not the x-axis. And now we're going to plug in 3. So 3 times 3 plus 1 over 6 times 3 minus 2, 4. So now we have 12 over 6, which equals 2. So at 3, our answer is 2. And we sketch that side of our graph in. I don't like these. I think they're fun. A little more interesting than lines and all that other boring stuff, don't you think? Okay, next is slant asymptote. This happens when the numerator, right here, is 1 degree larger than the denominator. So x squared is 1 degree larger than x. So when you went to do your horizontal, you had 2x squared over x, which gave you 2x. This means there is a slant asymptote. We still know at x minus 2 equals 0 that x equals 2 is undefined. And we'll have to factor the top to see if this helps us out or not. So first we got to find this slant asymptote. To do this, we do synthetic division. So we put our 2 here, 2, -5, 7 from our equation up here into our division. Drop the 2, multiply, add, multiply, add. No one actually cares about the remainder. It's what this is. So that's 2x minus 1. We got y equals 2x minus 1. This is your slant asymptote. It will always be a line. So now we go to -1 up 2 over 1 and draw in our slant. Now, if we look at our original, let's go back up just a tad. We have 2x squared minus 5x plus 7. Does this factor? 2x squared minus 5x plus 7. So let's multiply. We have 14x squared. Positive 7, that gives us -5. So it's got to add. That does not work. Since it does not work, that means that our 2 is truly an asymptote. So we're going to go to 2 and draw that one in. Now we're going to check a number on each side, which is 1 and 3. So I'm going to plug in 1 into the original and 3 into the original, since nothing reduced. So we're going to have 2 in up here. So we have 2 times 1 squared minus 5 times 1 plus 7 all over 1 minus 2. So 2 minus 5 plus 7, -3 plus 7 is 4 over -1, so we get -4. So we're going to go to -1. A quarter left. I do not know where it just went to. Sorry about that. I couldn't find where it went. So we went 1, -4. We put it on it. Now we approach the asymptotes. So we do the vertical asymptote and the slant asymptote. Now we check 3. It actually should end up in the other small area. So we plug in 3 into our original. So we have 2 times 3 squared, which is 9, minus 5 times 3, plus 7, all over 3 minus 2. So we got 18 minus 15 plus 7, which is 10. So now we go to 3 and 10, which is up here. And we sketch in our other side. Your graph is almost always going to be opposite on these times, not completely, but it is a good check. And then so like it could have also ended up, it did not this time, so the red one's wrong. Like it could have ended up on this side and then probably on the other large triangle. So don't think it always has to be in the little ones. It can be wherever it wants to go. Okay, next one is your turn. So give it a shot. Pause and try. Okay, I hope you did well. So first you did your horizontal and you got 3x, so you knew it was a slant, which means you had to do synthetic division, putting the 4 inside. You would have ignored your remainder. You had 3x plus 6, which equals y, which is your slant line. Next, we looked at the vertical, which is x minus 4, x equals 4. It did not cancel since this does not factor. So then we put in our vertical line at 4 right here. So x equals 4. Then we check 3 and 5 on each side. When you plugged in 3, you get 1. So 3, 1 is underneath the red one. So then you draw in your portion of the graph. Next, you plugged in 5. You got 5 at 35, which is way up here. Graph this here. And I know it's off your graph. Sorry about that. But it worked pretty well. I think you got the idea. All right, a little bit of together just to see what's happening. No actual math here. I'm going to give you a cost function. So a monthly fixed cost of $500 will increase $400 to produce each wheelchair. So it's 500 to start, 1,000 to start with, plus 400, and X is the number of wheelchairs. To find an average, you divide by your number, right? So you divide by X. So this C bar means average. So whenever you see a bar above, that means average. This happens to be a cost function average. So now I'm going to plug 1,000 in and see what my wheelchair cost is. So get up calculators, plug in 1,000 to the regular formula. So now we're going to end up with 500,000, maybe, plus 400,000. It is not writing. All over 1,000. Perhaps. Let's pause this. Okay, I think it's ready to work now. Maybe. So 500,000 plus your 400,000 all over your 1,000. When you did that, you should have got 900,000 divided by 1,000, giving you your cost is $900 to produce 1,000 wheelchairs. Now you're really going to up your game and start selling these things because they're so cool. And now you put in 10,000 for your X. So you got 500,000 plus 4 million all over 10,000. Whoops. I think I had too many zeros there. 10,000. There we go. Add and divide, and you should have came up with $450. Plug in 100,000, and you should have got 405. What is this doing? The more you get, the closer it gets to 400. So your horizontal asymptote is 400. So if you had a graph, you're here, $400,000 is your asymptote. You start down here, and then as you get this way, it approaches this $400 mark. It will never get lower than that. I mean, higher. I just did that backwards, I'm sorry. And it's approaching from the top. So it's going to approach from here, please, right? So it's going to approach from here and approach your $400 mark. So it will never get lower than that 400. Does that make sense? But it will get as close to as you can. So this means the minimum cost will be $400 to produce a wheelchair, or almost 400. And so the more you produce, the less you can sell them, or the least expensive they will. So more people can buy them. All right, pause and do your homework. Make sure you post discussion questions.